In this video, we're going to be using vectors to find speed and direction. So in this example, we're given that an airplane is traveling at a speed of 500 miles per hour with a bearing of 330 degrees at a fixed altitude with a negligible wind velocity, as shown in our first figure. And then we were reminded that from a previous section that in air navigation, bearings are measured in degrees clockwise from north, which means that we would start here and we'd go 330 degrees this way. So that's the 330 degrees that they're talking about there. But what does that convert to for us as far as our theta would be? And that's what this angle is right here, this 120 right there. That's our theta that we're going to be using. Okay, that's our theta. Now let's just look at this first vector for a moment. We know that we have a magnitude of 500 miles per hour because that's our speed right here. 500 miles per hour. So we can actually, our first vector, let's call it vector 1, so that we've got our magnitude 500 times the cosine of 120 degrees and the sine of 120 degrees. So we have that our first vector is 500 times the cosine of 120, comma 500 times the sine of 120. So before we simplify that any farther, why don't we look over at our, let's look at the rest of our problem. So we're given that the airplane is going to encounter wind blowing with a velocity of 70 miles per hour in a direction of north 45 degrees east, as shown in the second picture. Although I think that if we kind of think of it this way, look at it separately, if we're talking about just the wind, if the wind is blowing at north 45 degrees east, that means this is the velocity here of our wind, okay, of our wind's velocity. And so what's happening is this wind's velocity is pushing against the velocity of the airplane, which shifts it over, okay? So if I take my initial velocity for my airplane, or sorry, not velocity, vector, and I combine it with the vector of the wind, and I put them together, I get this new vector right here, right? This new vector right there. So what we're seeing right here, this little piece of orange right there, that's the wind blowing against my initial vector. So if this is my initial vector here, that's what this would be right here. So I put those together and it creates this vector v, my new vector for the airplane. So I know that I'm going to need a second vector, vector 2, that represents my wind, right? So we were told that that had a speed or velocity of 70 miles an hour, right? So that's going to be our magnitude of our second vector, of our wind vector. Now we know that because we're at north 45 degrees east, that the theta that we're going to be using here is going to be 45 degrees. And so as we finish writing this in component form, we've got the cosine of 45 and the sine of 45. All right, so we're a little out of room, so I'm going to go ahead and take all of this stuff right here, and we're just going to move it up here so we've got a little bit more room. So that means that our first vector, our airplane vector, is going to be 500 times negative 1/2 and 500 times radical 3 over 2. And I got those by looking at the unit circle and finding what the cosine of 120 was and what the sine of 120 was. So that's going to tell me that my initial airplane vector is going to be a negative 250, comma 250 times radical 3. So let's look over at our wind vector. And so our wind vector is going to be 70 times radical 2 over 2 and 70 times radical 2 over 2. And again, we got the radical 2 over 2's by looking at the unit circle and seeing what the cosine of 45 was, which was radical 2 over 2, and what the sine of 45 was, which was radical 2 over 2, which tells us that our wind vector equals 35 times radical 2, comma 35 times radical 2. Now, to find the velocity of our airplane in the wind, so I'm just going to call this just v, okay? That is going to be our initial vector, v, plus our vector for the wind, our v2. And so we've got that our vector v is going to be negative 250 plus 35 radical 2, comma 250 radical 3 plus 35 radical 2. And this is going to be our answer in exact form. We can't simplify it any farther because we cannot combine a radical 3 and a radical 2 through addition. But if we go ahead and we plug these into the calculator, and so we're going to get approximately a negative 200.5 and a 482.5. And now we're actually able to finish solving our question, which is what are the results, speeds, and direction of the airplane, which means that we're looking for the magnitude and our direction angle. So to find our magnitude of vector v, we're going to plug our components into our magnitude formula. So, which gives us the square root of negative 200.5 squared plus 482.5 squared. And if we plug that into the calculator, we're going to see that we're going to get a resultant speed of the airplane as approximately 522.5 miles per hour. And so that's our speed. So now we want to find our direction angle. Now if we look at what we were given, we see that over here we're in the second quadrant, which means that the angle that we find is going to be a reference angle, and then we're going to have to find our angle from that. So remember that we have the tangent of theta is going to be our b component divided by our a component. And so if we go ahead and if we find the inverse tangent of that, we're going to find that our reference angle is going to be approximately 67.4 degrees. And so remember, we want to know what our actual angle is from 0. And so we're going to take the 180 degrees that we would have over here, right, that 180 degrees, and we're going to subtract our reference angle, and that's going to give us our theta, right? So theta is going to be our 180 degrees minus our reference angle. And so if we plug that in, 180 minus 67.4, we're going to get 112.6 degrees. And so now we have found our speed of our aircraft, and we have also found the direction of our airplane. And we're finished.